Okay, let's get started. So today's lecture is about homotopic equivalences, but it's so much more than about homotopic equivalences. I will try to explain the relevance of why we bother with homotopic equivalences and the difference between isomorphism and equivalence and so on, because I think the reasons run deep and also the applications from the point of view of foundations of mathematics. But as usual, let us start with the review. Hello. I can't do this when the notebook is on my right. It's unnatural for some reason. There we go. The last thing we talked about were homotopy levels. And in particular, we started counting at the ridiculous number -2. And we had the homotopy level of -2, or the contractible spaces. So this means spaces with, the way to understand this is to say that it has exactly one point. And then the next level, -1, were the propositions. And the way to understand this one was at most one point. We're careful the way that you need to understand this, because everything is up to homotopy, is to say not exactly one point, but exactly one point up to homotopy, so up to path invariance, right? So the statement was, there is a point such that every other point is equal to it. Right? That was the meaning of there was of contractible, so up to homotopy, so up to. When we say exactly one point, so just we have to get used to that. Okay, so then there was level 0, and these were sets. And the way to understand sets is to say space whose path spaces are propositions. Because that's the general recursive definition. You're at level n+1 if your path spaces are at level n. And then groupoids was the next one. So we could keep saying these things, but they're not very illuminating. Space whose path spaces are sets, and so on and so on. And so we have we have exposed a hierarchy of concepts. We just formalized homotopy theoretic complexity. A contractible space is, from the homotopy from the homotopy theory point of view, a contractible space is a really boring thing. And then when you have, but it's also fundamental in many respects. And then propositions are slightly less boring because they have at most one point. And if you work this out homotopy theoretically, so this was to have one point in type theory corresponds to contractibility because everything is up to paths. And so you see that you get we described homotopy theoretic complexity, but we are really getting notions which are very familiar also from foundations of mathematics, namely these two. Propositions are truth values, and that's the level of logic. And yes, and last time we used truncation to actually encode logic into type theory using the Curry-Howard correspondence, the modified, where we truncated exists. So to get exists and or, we use the abstract exists and abstract or. So logic appeared, and also sets, because the sets in one way or another always try to capture the idea that a space is made of, that the essential thing about a space are its elements. That's extensionality. The extensionality principle of set for sets says that, for instance, it's not important any kind of metric or multiplicity of points. None of that is there. So this is the level of sets, and then what you see appearing up here is maybe more like, it starts to look more like a little bit about category theory, but eventually it just turns into homotopic theory because, of course, this is homotopic theory. Now, let's spend some time with these levels -1 and 0, because there is something to be explained here, which I think is exposed inside homotopy type theory very nicely, and is maybe not so visible when you just do foundations using logic and sets, or objects and logic, or what you have, like these other ways. And the thing that I want to discuss is the idea of structure versus property. So this is something that we're going to make precise, technically precise. We can in homotopy type theory easily, so maybe not so easily in some other setting, but it's of course still possible. So the structure versus property thing is a general phenomenon that a mathematician must pay attention to, because if you get these things wrong, you suffer and you don't necessarily know why you're suffering. So what is going on? So when you study some mathematical object, whatever your structure is, it is important that it is clear what the structure is. That is to say, you should, if there's some other relevant structure hidden somewhere and you don't notice it, things are likely going to go wrong. So for instance, you might not notice something and then you don't know how to prove things. Let me give you an example. Suppose you're working, the examples are going to be silly, but you can imagine more complex examples that could hinder development for a while. Suppose you are doing complex analysis and you've never noticed that there is an involution, the conjugate value on complex numbers. That is an important part of the structure of complex numbers, namely that you can conjugate complex numbers. If you're not aware of this fact, and then you're likely thinking that the complex numbers are something like a ring or a field, but it's certainly a missed opportunity, and there will be lots and lots of things that you will not do because you don't know about this extra structure. Sometimes it is important not, so that's like having a structure that you didn't observe, that you were not aware of. It's probably a bad idea. You should be aware of it. Sometimes there is structure that you don't want, and then you want to somehow get rid of it. So an example of that would be, suppose you're trying to shoot for something like topology, but the only way that you know how to state topology is using metric and open balls. Okay? So the only examples of topological spaces that you have ever seen in your life were metric spaces. So you naturally think that the only way to do topology is to use distance. Now, distance is going to get in the way because it's structure that you're not trying to capture, but it's there. If you're trying to do topology, you should ignore distance up to a point. It's kind of subtle. You cannot just remove distance. You need the distance to get the notion of an open ball, but after that, for instance, the notion of a continuous function does not really depend on distance. It depends on what the open balls are. So that would be an example where things could go wrong if you have extra structure and it's somehow hanging around and it shouldn't be there, and then maybe it's getting in the way and it's complicating things, and things are not as nice as they could be if you could get rid of the structure. So having structure or not having structure, this is a very important thing. And so in general, let's look at an example of how we do this. Okay, so example. So after this, to arrive at these notions, so sort of from another direction, let's look at an example. And so, you can't really do. I don't think you can do foundations of mathematics unless you have somewhere as an example groups. Right? Groups needs to be an example, or you can't do algebra. So example. Let's take groups. How will we formulate groups in homotopy type theory. Okay, so in homotopy type theory, everything is a space. So yeah, a group is going to be a space, but more importantly, the totality of all groups is also going to be some sort of a really large space. Just like all groups in set theory form a class, so here they're going to form a big type. So let's try to write down the type. Okay, so how would you write down the type of all groups, not a single group, but all of them? Okay, so what's all groups? So the type of all groups living in a certain universe of all groups. Well, you would do it like this. You would say it's some big type called group, obviously. And we define this to be, well, what now you just start, what is it going to be? Well, it's a tuple, right? So a group is a set and some operations on the set and so on, right? So it's a tuple of things. So a tuple, but they depend. You pick a carrier set and then the operation depends on the carrier set. So it's going to be a dependent tuple, therefore a dependent sum. So you start writing things like this. You say it's a sum of things. So first we have a carrier, which is going to be a type in the universe, some universe that we work in, and then it's going to be, now we need what? Well, we need a special element called unit, so we say there's going to be also an element. So I think, these are iterated sums. I'm not writing sum here. Yeah? G, yes, thank you. This one is G. And then there is an operation called M, let's call it M, which goes from G to G, G cross G to G, and there is another operation I, which goes from G to G. Of course, this will be the multiplication and the inverse, and this is going to be the unit. And now we have to explain that, well, we have to have now something that says that this thing forms a group. Classically, so far, this would be part of the structure. That is to say, you would have a carrier set and some operations, and then the rest are axioms that need to be satisfied. So let's just write them. There's no space here. Let me write it like this: is group, and now all these things together: G, E, M, I, and now down here we can define is group. Is group G, E, M, I, and it's painful, but I'm going to write it down. Is. So now I will just write down the axioms for a group, but because we could do it either using the logical, we could either use the logical notation from last time. For all is just pi, and is just cross, right? It doesn't matter because we're only going to use for all and equations. So I'm going to use pi's. Just because I want to train everybody in reading type theoretic statements, but you can read this, of course, it can be read as for all. So what would these be? Okay, let's write them down. So the first one will be that pi x, y, z in G, m, x, y, z equals in G, so m, x, m, y, z. That's the first one. It's associativity of multiplication times. And then we have one that speaks about the inverse and the unit. So maybe I can organize myself like this. So one of them will be mxe equals. So all the equations are in G. So I'm not going to, I'll drop these subscripts. Mx equals x and mex equals x. And mxi of x equals e, and mi of x equals e. So maybe this. Yeah. So this is precisely what I was saying. I wouldn't do, but these are just aliases for times. But let me use times. So now the times is going to look a lot like x. So let me do it like this. Times. I don't know what you prefer. Okay. So this is a very good attempt. And because it just transcribes the usual definition of group into type theory. We have a huge type group, and so an element, what is going to be an element of, what is an element of this type? It's 1, 2, 3, 4, 5. It's a quintuple, but actually here you have a further product, so it's more like a sextuple of things, of which the first 4 are the structure, and then the remaining ones are elements, points of this space. So what is this space? Well, this is a space which has some paths, some functions giving you paths, so it corresponds to the usual axioms. Now, this definition is wrong, and this is not. This is far from. It's not so easy to see that this is going to be wrong in type theory. So let's explain why it's wrong. So first of all, let me show you the problem. Okay. So when you develop your type theory, you are eventually going to hit the following question. You're going to say, aha, I have. So by the way, now I'm going to write. I think it's. No, I did something bad. Okay. I think I'm going to like this. Write mxy just as usual as just xy or x times y. Okay. So we can have the following. Let's see. We have associativity for 3 elements, but from associativity for 3 elements, you can get associativity for 4 elements. So you know that if I start like this, x, y associated to the left, x, y, z, t, this should be equal to x, the other one, right? x, y, z, t. Okay, let's be a little bit careful how we do this. Well, because if we have a group, we're going to have a function here which allows us to reassociate 3 elements. So how do you get from here to here? So there are 2 ways to get here from here to here. So first of all, you can have a path from this element, and I reassociate on the inside. So I'm going to get x, y, z, t. And now I reassociate on the outside. What am I doing? X, y, z, t. Yes, and so the next one is x, y, z. If I make a mistake, please let me know. So so here I reassociated the 3 on the inside. Here I took x times middle one times the other one, and I reassociated. So am I missing a parenthesis? And now I can just reassociate on the inside on the right, see, because then I get the desired one, okay? And so these will be 3 applications of reassociate. I will use the associative law 3 times. But I can also do it in another way. I can first reassociate on the outside, and then I will get x, y, z, t. That's also one way of reassociating. And now I can just, the remaining step is just reassociate here, this guy, and so I will get here this. It's a pentagon. It's the dreaded okay, so this is a dreaded pentagon. Is there anything? So if we write, here we're going to have some function here. Let's call it alpha for the associator. This bit here will be some alpha. So here it's alpha applied to something. So these are different applications of alpha. And you can say, wait a minute, but aren't these two, so I have paths. I have a path from here to here. I have 2 paths from here to here. Are they equal? This is something that you never ever even ask when you do ordinary group theory. When you do ordinary group theory, you just prove equations. You don't worry how you prove the equations. But here we have 2 paths, each showing us how to prove that the top equals the bottom. And maybe they're different. Maybe there is nothing in this definition that forces them to be equal. Now, there are several possible reactions to this. Maybe it doesn't matter. But it turns out that it matters, because you get stuck, and you get stuck quickly if you don't believe this. You start formalizing group theory in Cauchy, and you will get stuck, because what will happen is that in one lemma you will prove associativity one way, in another lemma you will prove associativity in another way, and then because of that something won't fit, because you're going to have a dependent type which depends on these elements, and then you will transport via one of these paths versus the other. You will get two elements which are not exactly the same, and you will not know whether they're the same, because you don't know whether these two paths are equal, whether there is a homotopy between them. And it is going to be a real problem. And what we see here is unintended additional structure. Group theory, as it is usually conceived, does not worry about how or why things are equal. Two elements in a group, when they say they are equal, you prove they're equal, you're done. You don't worry about how you prove they're equal. They're now equal. Here, you need to worry. There are different paths between the elements of the group, and maybe it matters which one you took. So, what is going on? You have to look at this definition and say, whenever I see distinctions where I expected no distinctions, if somehow magically something starts to matter when it shouldn't, that's a sign of unintended extra structure. For instance, if you're doing your topology using metrics, at some point you're going to say, but this is very annoying, distance shouldn't matter so much. And that will be a sign of unintended extra structure. So, something is going on. We have too much structure. This is not a group. A group does not have a structure that involves the associativity pentagon. This is not something that group theorists study. There are other people who study this. Higher category theory people, 2 categories, 3 categories, infinity categories, right? So they study this, and it's a very familiar pentagon for them. So we are not hitting the right kind of structure. This is something like an infinity group or God knows what. We don't know, because maybe we have to read very, very thick books written by Lurie or something to find out what this is. We don't know right now. But what we do see is we don't want this. So the question is, how do we fix it? Well, how do you fix it if you have too much structure? So there are some typical moves you can make. First of all, if you have too much structure, you can try to make a quotient so that things which are supposed to be equivalent but aren't become equivalent. Sometimes this is an option. So an example would be you're trying to construct real numbers, and you have the great idea that a real number is the same thing as a Cauchy sequence of rationals. Suddenly you have too much structure, because there are different sequences, Cauchy sequences, all converging to 0, all representing what you think should be the same real number. But now you suddenly have lots of zeros. You have zeros that converge this fast, and you have another 0 that converges with some other speed, and you have a 0 which converges from the positive side. And you don't want all these zeros, so you quotient. So you say the real numbers are Cauchy sequences quotiented by an equivalence relation, which makes two Cauchy sequences equal when something, for instance, when if you interleave them, it's still a Cauchy sequence. So that would be one possibility. That's one possibility, so we could try to quotient something here. Another possibility is that, which we do have at our disposal in type theory, because we have homotopy levels, is to say, well, we should maybe just control at what level these things land in. So maybe some of these types should be sets, or maybe some of these types should be propositions. It's a bit weird that we took what is normally a proposition, a logical statement, in the usual foundations of mathematics. This would be a set, these would be functions, and this wouldn't be a set. This is a logical formula. It's a bunch of axioms. So it's a bit weird that we took axioms and we turn them into a general space. So it looks like maybe we should require that this stuff here should be a proposition. It should be at h level -1. It shouldn't be just at some arbitrary level. So that would be another way to do this. So that's completely reasonable. You can think of this also in some other more traditional way. For instance, you could say, okay, suppose we want to do topological groups. Well, there, if it's topological groups, it's fair point to ask whether the axioms for a group should hold really, really, or only up to a path. And that would be a question of what kind of groups you get when you do topological groups. Do you want equations to hold really, really, so on the nose, or maybe only up to a path? But if you say up to a path, you will immediately hit extra structure because you will ask, which path? Because there will be lots of paths. So this sort of thinking, while it's more unusual in other frameworks, can still be present. And it's sometimes very, very important to get your mathematical structures correct and your theory working. So what's the solution here? So this is wrong. Wrong because there is nothing saying that these two are equal. So solution, we want to make sure that what? Well, make sure that this is equal, that these two paths are equal. Well, actually make sure that any two parallel paths are equal. Right? So then you will never, I don't want to worry about paths in a group. That's not what groups are about. How do I say that I don't worry about paths in a group? I say a group doesn't have any interesting paths. How do I say that a group doesn't have any interesting paths? It's a set. So make sure that G is a set. So the new and improved definition is a group is, now I don't say G is from a universe, I say G is a set or a zero type. And then you go on. But this is what changed. This is the change. And then everything will be fine, because if G is a zero type, then by definition that means that equality in G is a proposition. So this is a proposition, and then you need a bunch of lemmas. Like if you have a pi of a proposition, it's a proposition. Product of propositions is a proposition, and so on. And then you easily prove that this is a proposition. So that's a lesson to be learned about structure versus property and how we have to pay attention to these things. There are other examples, of course. So maybe I can just quickly say, what are some other examples where you need to pay attention? By the way, so if you think about these things, you will find examples in whatever area of mathematics you work in. So typically, it'll be something like, instead of saying the two things are isomorphic, you need to say which isomorphism you have in mind, things like that. Or instead of saying that two things are holomorphic, you need to pay attention to which holomorphic function. So things of that kind are pointing to the fact that you maybe want to have structure instead of property, or vice versa. Other examples, okay? So in general, we can easily generalize this for algebraic structures. Say rings, modules. Rings, modules. The carrier, you hit exactly the same problem. The carrier type should be a set. Another one that I can mention is when you define a category. When you define what a category is, well, how do you define what a category is? We say, well, we have C0, which is a type, right, of objects, the space of objects, or the type of objects. And then you say, well, there's C1, which is the morphisms. Now there are several ways to do this, but you do it like this. You say, if you give me two objects, I will give you the morphisms between them. And so here is where you can make a mistake. So you say, what are the morphisms between two objects? The type of morphisms between two objects. If you say that it's just a general type, you will make a mistake because you will have the exact associativity problem again at the level of morphisms. So you need to say here it's a zero type, a set. So you need to pay attention and you need to do this. Right. Yeah, this would be now, well, now of course, I mean, this is, as usual, you get questions of universes when you speak about categories. Do you small categories, categories in some universe, la 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 la. So this zero type would be the zero type with respect to this particular U probably. But you could also consider, if you have lots of universes, you get to play. You say, well, you know, the objects are from some universe and then the morphisms are from some other universe, and you can study these interactions. I don't think it's going to be super interesting.
Smallness doesn't mean it's not the same thing as having low H level.
Yeah, okay, so maybe that's something we need to pay. Yeah, so that's something that I need to explicitly emphasize. So this is the space of morphisms, namely C1AB, the space of morphisms from A to B, and you want this one to be a set. Otherwise, you get into trouble. So that's another example where you need to pay attention. Yes, maybe this is, so when we write something like zero type, this is a bit imprecise, because how did we define this? We define this as those types X in a universe such that it has H level, such that is set, whatever it was, is set X. And so this really, it would be more appropriate to parameterize this by the U. See, the picture is like this. You have your universe U. U is my universe, and inside this universe I have level 0, level 1, level 2, and so on. All the finite levels, and then there will be here some stuff which is at no level at all, okay? Which is outside of every level. There may be something. So here will be the levels. So these would be the propositions in U. And did I just switch back to Voivodsky? Yes, I did. I need to start with -2 to be consistent with myself. Well, that one was right. -2, -1, 0, the levels, right? And so these are props, these are sets, and so on. And each universe has one of these, right? Levels. So if I take a different universe, it's going to have its own gradation. So maybe it's a bigger universe, so it contains the previous ones, but the point is there are two dimensions here to complexity. One is size, which is which universe you're in, and the other one is complex homotopic theoretic complexity. How complex are your path spaces? So that's the other one. Okay, any questions? I can give you another example, which is maybe where you have to pay attention. And this example comes from the fact, you will see that this is also it happens in other places. So let's see another example. If you imagine for a moment that we have defined rational numbers, okay? What is a Cauchy sequence? So a Cauchy sequence, well, let's write down the definition. A Cauchy sequence, so when is A from N to Q a Cauchy sequence? Well, okay, so for every epsilon greater than 0, there exists N such that for all N and M, bad idea, for all m and k greater than or equal to n, am minus ak is less than epsilon. There are many ways to write this equivalently. Let's just stick with this one, because this happens to be what Professor Globeunik taught me. And now you look at this and you say, how are we going to translate this into type theory? Well, for all is just pi, and we don't have to change this, and you were assuming we know what this less than means and so on. But this exists is interesting, because it could be sigma or it could be truncated sigma. So there would be two options. So I could write this one as follows. I could say pi epsilon greater than 0, and then here sigma n in n such that pi mk greater than 0 am minus. It's not entirely formal here, so you might be wondering, how do I intend to formulate this? And it's a good question, and you should figure it out. But what will be the difference between these two? So this one is truncated sigma, and this one is non-truncated sigma. The difference is going to be that in one case, namely here, we get a function which assigns, see, because an element of this is going to be a function f. So what is an element of this? It's a function c, witnessing that A is a Cauchy sequence. But this c of epsilon, well, c of epsilon, is going to be a tuple of things. So it's going to be some n epsilon here and blah, 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 blah. So this n epsilon, this is just pi 1 of c epsilon. The point is that I get a function which, given an epsilon, gives me a suitable n. But up here, given a function, I get the truncated version, so I don't know what number it is. I don't have the number as a function, and this could matter. This is again a question of property versus structure. If you take this definition here, then to be a sequence can be a Cauchy sequence in many ways, because each C here will give me another way in which A is a Cauchy sequence. And this is going to show, because if I have different C's, I might have different ideas about how fast is the convergence of A. If I get a really lousy C, which isn't optimal, I won't be, calculating with A, maybe a little more inefficient. And this actually happens in implementations of exact real arithmetic. It is a common phenomenon, also in numerical methods. It is a common phenomenon that you have a numerical procedure and you estimate how fast it converges. And if your estimate is bad, then you are a very pessimistic person. You think, oh yeah, but maybe we have to calculate this many iterations, where in fact many fewer iterations would help. This is just property versus structure in practice. If you're doing numerical calculations and you care about the rate of convergence, then maybe the second definition is the better one for you, because it allows you to explicitly talk about the rate of convergence. This C is also sometimes called the modulus of Cauchiness or the modulus of convergence or some such thing. So depending on what you're doing, you need one or the other. You need to be sensitive to these things. When you define the type of Cauchy sequences, it may be a really bad idea to use the second definition, because then you will have, whenever you have a Cauchy sequence, you will have to worry about in what way is it Cauchy, because there are many ways in which it can be a Cauchy sequence, because there are many C's. But the first one, you can show that it's a proposition, so all the ways of being Cauchy are the same. So we arrive here at something slightly deeper, namely, this is a discussion about proof relevance. So what is proof relevance? I like to joke that the most central notion of mathematics, which is the proof, is irrelevant to mathematics. And what I mean by that is that we make proofs, but we never do anything with them. Once a proof is made, you just say, okay, and you throw it away. You never say a space of proofs. If you do anything with a proof, you do it at an informal level. So it's all, unless you're a logician, right? And then you're like, proof is a syntactic tree, la la la. Okay, so then you do something. But what we are discussing now is that not so much that proofs as syntactic objects are important. We're discussing the fact that proofs as witnesses to a structure are maybe important, and it is important in which way you construct. Okay, so it's obviously important in which way you construct some element of a space, because if you're constructing a real number, it's likely going to matter whether you've constructed 7 or 42. It's not the same thing. But here, because everything is a construction, in principle, proofs, some of the things that we call proof turn out to be constructions, and others, so turn out to be elements of types, and others turn out to be of elements of types which happen to be propositions. So I think to make this very proper, let us say that a proof is a construction of a point of a type which happens to be a proposition. It needs to be a proposition. You don't call it a proof if it's not a proposition, except that that's not what mathematical practice does. In mathematical practice, you open a book, very, very often, what you read is the following. Theorem. There exists an element of blah, 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 blah. So it's an existence statement. Proof. Some proof. Okay, something. In this something, they very obviously construct one of these things. Moreover, later on, they use the thing they constructed in the proof. Well, if a proof really were an element of a proposition, then it would be all the constructions ought to be the same. So you look at a book, you look at a paper, you look at the proof. If the rest of the paper depends on which proof it is, for instance, which witnesses of existence they constructed, which isomorphism they used. If the rest of the paper depends on what they did in the proof, then it was not a proof. They only called it a proof. It was a construction, but they called it a proof. Why? Because they didn't have homotopy type theory. So poor guys couldn't call it properly. So it should be called something else. So let us say that it is a proof if it is a construction of a type in a type that happens to be a proposition. Otherwise, it's not a proof. Otherwise, it's a construction. So pay attention in your mathematical practice. If it's not a proof, don't call it a proof. So, but then the question is, what should you call it? Vladimir Voevodsky suggested that when you have something that says theorem, blah, 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 proof, but you notice that it's not really a proposition, and it's not really an element of a proposition, you should instead say problem. You write down the type of the problem, construction, or solution. Or solution. Because then it's clear that you have a particular solution. Of course there can be several solutions and they will be different. Or it's even more, it's better to call it construction, because then there will be several constructions for this problem. You want an equilateral triangle on a given segment. If it's a proof, then you need to worry about the fact that there are two solutions. If it's a construction, you don't have to worry about the fact that each segment has two solutions. So you need to do something there, okay? Just to finish this lecture, the first part. So let's call it, so we need to pay attention to property of points of some space A is what? Is a dependent type P, which goes from A into propositions. Prop, which is just prop, for me now is just going to be an abbreviation for -1 types because I feel silly writing down -1 types. Okay. Structure on A, or depending on points on A, is a dependent type. P, which goes from A to the universe. So general universe. And you might further, right? For every point, it gives me a space of possibilities. So here, why is this reasonable? Because if now I have x in A, okay, then I can look at P of x. And if P of x is a prop, that means there is only one way. All the elements of P of x are the same. So there is only one way in which I can have this P of x. Okay? But if P of x is a type, there can be several ways, several structures over x. So for instance, x could be a segment on the plane. P of x could be the space of equilateral triangles who have that segment as one of the sides. That would be a structure because I would always have 2 triangles here. I wouldn't have 1. If I truncate and I say it exists, then it becomes 1. Okay. So let's have a break, and then we are going to speak about... Actually, no, let's not have a break, because I have just one other example which I want to show you just to finish this idea of group theory. So this isn't really doing anything here, so I think this was uninformative. So another example. It's an example of this, did they do a theorem or did they do a proof? Okay, so you can open a book, and depending on how carefully it's written, you might see this theorem formulated with several degrees of freedom. For a group homomorphism F from G to H, okay, we have the G quotiented by the kernel of H. Can you finish the theorem for me? Is isomorphic to, as a group, to the image of F. This is what the first isomorphism theorem. It's one of the isomorphism theorems. Okay. Is that what they want? Typically, no. But you might see it said this way. Why not? What you need to worry about here is there more than one way to do this? Okay, given a homomorphism F, the thing to ask is here, is there more than one way in which 2 groups can be isomorphic? Yes. So, you look at the proof. If everybody uses always the same isomorphism here, then it's very likely that this was not the right theorem. They will rely on the particular isomorphism that they produced. So in that case, you need to say, no, but better theorem is for a group homomorphism Fg to H, the canonical map from G kernel F to the image of F is an isomorphism. And then the question is, what is this canonical map? And so you need to like wave your hands and explain what, or maybe better not wave your hands, explain what this canonical map is. But there is going to be a canonical map like that. You can draw a little diagram and you chase some quotients and you get the canonical map, okay? But the difference now is, here we didn't say which map is supposed to be an isomorphism. And here we're saying that it's a particular one. So speaking very precisely, this might be exactly the kind of thing that distinguishes, in some places, property versus structure. So this is very clearly structure. This thing here, this is extra structure because two groups, if you have two groups, I don't know, G and H, or if you have just two groups A and B, there can have many points. There can be many isomorphisms from A to B. So this is structure. So then, but this begs the question as to, so maybe is an isomorphism is a property. Well, that's something that we're going to do after the break. But here is the question. So just at the level of sets and functions, can a function be an isomorphism in several ways? For instance, can a homomorphism between groups have several inverses? Or if it has one, it has at most one, right? So if you have a homomorphism between groups, everybody knows that it has at most one inverse. So it sounds like it's a property. Wrong. It's not, unless we're careful. So, well, in the case of groups, now that we have the correct definition of group, it will be. But in general, no. So this is something that we're going to do next, is to explain the difference between isomorphism and homotopic equivalence and why one of them is preferred to the other. But we have a break first. So let's look at isomorphisms. And this is also the beginning of the next section, which I'm going to start on a new page. Oh, maybe just one more political comment. Okay, so we discovered something here, namely the difference between property and structure. Of course, people have known about this difference for a long time. We're not the first ones to discover the difference. What I'm pointing out is that this difference fits fairly naturally in these homotopy levels of type theory. Why is this important in this particular case? Because you need this sort of thing to successfully formalize mathematics. If you have informal mathematics in which the difference between property and structure is somewhat obscure inside the natural language and is not mathematically apparent from the text, but it is present in the culture. So for instance, the first isomorphism theorem or some might be written like this, but everybody knows that you always take a particular isomorphism here that is a piece of mathematics which is present in the culture but is not made very explicit. And once you start formalizing mathematics with computers, this becomes very, very annoying because you need to reverse engineer lots of this stuff. So now if you're a computer scientist who is well versed in formalization of mathematics, trying to penetrate a mathematical subject in which, say, 5% or 2% of mathematical knowledge is implicit in the way they say things, but they mean something else, those 2% might represent 30% of your formalization effort. That's why I think it is important to be aware of these differences. It's not just, some sort of philosophical fetish, although philosophical fetishes are a nice thing. But in addition to just it being philosophical fetish, it also has these sorts of things, not this particular one, but similar phenomena, which were implicit in mathematics, had to be made explicit in some of the big formalization problems, efforts that happened. And it's interesting to speak to the people and to read what they had to write about those things. Sometimes the proof method was far from apparent, but everybody understood that it was a proof. But it took a while to figure out for an outsider to what the hell they were doing. So, you know, it's good to pay attention to details. Okay, so with that said, let's have a look at isomorphisms. But the title is Equivalences, of course. Okay, so suppose we have a map F from X to Y, and let's write down what it means for it to be an isomorphism. So is iso, and we're just going to turn the usual definition into type theory naively. So we're going to say, well, to be an isomorphism, there needs to be a map G from Y to X such that G composed with F equals identity on X and F composed with G equals identity on Y. So, is this a property of F or is this structure on F? To ask in another way, can F be an isomorphism in many ways? So let's see. Okay, so first of all, what is an element? So what we're wondering about is iso F a proposition? Recall what it means for something to be a proposition. A type is a proposition if any 2 points of the type are equal. So we are asking, is it the case that if I take 2 points of this type, they're equal? So let's take 2 points of this type. So you might have G. So what is an element of this type? It's a dependent sum. So it's a tuple. The first component is a map. And then the second component is actually 2 more components, and they are paths. There is a path. Where do these paths happen, by the way? So this path happens in X arrow X, and this path happens in Y arrow Y. So it's G and 2 paths. Let me call them, I don't know. Let me call 2, let's say, suppose I have 2 of them. I have G1, and then I have eta1, and I have theta1. And this is an element of is iso of F. And then suppose I have G2, eta2, theta2, which is an is iso of F. So what does this mean? Let me write down the type of eta1. So eta1 is in here. So it's a path which goes from G to F, G composed with F to identity on X. And similarly for the others. Okay. G1. G1 here, yes. Thank you. Okay, so now we wonder whether these 2 guys are equal. So for the first components, what can be said? So first components, so is it the case that G1 equals G2? When you say that, because this is a type, let's practice this a little bit, this is a type, when you say that, you're really asking, do we know of any points in this type? Do we know of any paths between G1 and G2? And what can be done and it's not difficult, and this was going to be an exercise, is this. You can show that there is an element of for all x in y, sorry, and then obviously it needs to be a y. For all y in y, G1 of y equals G2 of y. This we can get from this. An element like this can be had from this eta1, theta1, eta2, theta2 business exercise. You take the usual proof, you just convert it. Okay. So it's not quite. So let's observe the difference. Okay. So this thing here says there is a path. This thing here says for every point there is a path between the corresponding values. So let us define homotopies. So if I have now two general maps, let's see, I have F and G. I will now invent two different letters, say U and V, from A to B is a point of, for all A in A, U of A equals in B, V of B. And we are going V of A. And we're going to give a name to this. We're going to have a notation. Let's write it like this: U, V. Okay. By definition. So U, V is this space. So this is the space of homotopies. So a homotopy is this pointwise equality thing. Pointwise paths versus real paths. And so what you can get, so the question then, if you skip here, is it the case that if G1 is homotopic to G2, then there is a path from G1 to G2. And what is this? Well, this is just extensionality of functions. So maybe I can spend a minute on this idea. This is something that is very familiar to mathematicians, and it comes in different shapes and forms. It's called extensionality. Namely that a mathematical object is determined by all the ways that it can be inspected or used, or all the ways that information can be extracted from it. So examples would be sets have an axiom of extensionality stating that two sets are equal if they have the same elements. So a basic observation about a set is that some element belongs to it. That's a basic observation about an element, and then this is saying sets are equal if they have the same elements. If they have all the same observations, if they satisfy the same basic observations, then they're equal. So that's set extensionality. Function extensionality is precisely this implication. It says if two functions always give you the same result when applied to the same value argument, then they're equal. And that's function extensionality. So how could function extensionality fail? Not so easily for a mathematician. Mathematics really relies quite deeply on the fact that functions are extensional. But in computer science, this will easily be broken, because in computer science you might have a strange idea that when you have a function, maybe you care about how fast it is. And so you could have a function, you have two functions which give you the same result, but one of them takes longer. And so then it would not be entirely natural to think that both are equal in such a case. There could be other questions about the resources or who knows what. So, you could imagine some sort of computer science reason why you don't want this property, but we want them. We want this property because otherwise it's very difficult to do mathematics. And so we have this principle called function extensionality. By the way, observe that set extensionality is not something that just translates to type extensionality, because type extensionality would say if two types have equal points, then they're equal. Yeah? That doesn't make any sense, because a point can always, by construction, only exist in one space. So you cannot even begin to say type extensionality in this form. At least not by saying if two types have the same points, then they're equal. That just doesn't exist. Okay. So function extensionality says, let's write it down. Well, so it says, let's write it down in full. So pi, if I have x and y, which are two types, and then I have two maps f and g, which go from x to y, and then if I know that for every x in x, f of x equals g of x, then f equals g. And this is the type of function extensionality. And to say that we assume function extensionality is to say there is some point here which we call funnext. Okay? That's what it means to assume that this holds. Let me tell you a little bit about the meta theory of this. So first of all, in type theory, you cannot show, it is impossible to prove that this type has a point. Nevertheless, there are many models in which this happens, so it is consistent to assume this. Assuming function extensionality will not produce a contradiction, unless you also assume something totally crazy in addition to function extensionality, but it will not produce a contradiction. It is mathematically extremely desirable, and therefore we are going to use it. Later on, we're going to see that univalence applies function extensionality, and so that's another reason why there is no harm in using function extensionality, because we intend to use univalence as well. But there should be a nagging concern at this point if you're learning well today. It should be, is this property or structure? Namely, does this space possibly have several points? And if it has many points, are they equal? Or could they be different? Could function extensionality hold in several different ways? And that is a valid concern. And so if you studied this seriously, say in 2013, 12, right, then you would worry about this and you would want to prove lemmas, which means that you have to now go to the hot book and see what it has to say about it. But it is a valid concern. I want to raise the concern. I want to enhance your sensibilities as to property versus structure. When somebody says something like this, you say, which funnext? Can there be many? Prove a lemma. Prove to me that this is a property. Maybe this is a property of the universe U. Okay? So, with function extensionality, so now using function extensionality, thus using funnext, we can indeed show that G1 equals G2. This is from up here. Up here. So this is continuing from star. But we're still left, now that we're going to get a path, where is this? We're going to get a path from G1 to G2, but we still have other components to worry about. You see, you don't just worry about G1 and G2 if you want to show that this is an isomorphism, then you also need to now, well, you might be tempted to say eta 1 equals eta 2, but that's not quite right because they don't live at the same type. Eta 1 lives at G1 composed with F equals id x, and eta 2 lives at G2 composed with F equals id x. And so you cannot say that they're equal because they're not even in the same type. So what you need to do is, you need to take this equality between G1 and G2 that we just constructed and transport eta 1 along the equality over here and then compare. That's what needs to happen. You wouldn't want to do this on your first try by yourself on paper. You either want to get frustrated by a proof assistant or by a human who can do it. And I was thinking maybe I could have like a sort of an exercise session. I think it would be very useful, where we do some of these details. They're time consuming and they must be done interactively. If I show you all the details here now, you will just go like whoop and your brain will turn off. At least mine would. So you want to do this interactively, where you're doing it and somebody is sort of prodding you along. It's like, now do this, now do that. And you have to do it with your own speed. So in any case, the point is that while we can show that the first two components are equal, we need to still worry about so here we're going to have a path here. We're going to have some path P to show that if we transport using P eta 1, that's going to be equal to eta 2, and then similarly for the thetas, okay? So this still needs to be done, and it cannot be done in general. This cannot be done. So is iso, and in fact, assuming univalence, in the hot book you have a counter example. You have a type which actually isn't like this. So this is not a proposition, is not in general a proposition. We failed to prove it, and moreover, the hot book has an actual counterexample using univalence. So because it's not a proposition, this means that if we try to do mathematics using this definition of isomorphism, we are looking for trouble. We're looking for trouble because in ordinary mathematics, which has an enormous amount of material built up, isomorphism is a property. It's not a structure. People never discuss in what way is the, F is F can be an isomorphism in, in this many ways. They don't say that. It's a property. So, I mean, there are corners of mathematics when they say that, of course, homotopy theory and higher category theory and so on. There's always some corner that's an example, that's a counterexample. But for the main development, it's not like that. We need it to be a proposition. And so we need to improve this. So need to improve this. And this was one of the main contributions of Vladimir Voevodsky to have defined this notion. And so let's do it. So first we will need, so what is going on when you analyze this? Okay, so why is it a structure? Why isn't it a proposition? And the way you think about it is as follows. This is a space. Is iso F is a space. It may have several points and therefore is not a proposition. There could be many interesting points in it. How do we improve it? One possibility is that we try to squish things together, but another one is that we try to enrich the space so that it becomes contractible. Okay? Let me give you a super silly example. Okay? Take the space of all integers between 0 and 7. Okay? That's not a proposition. It's got many points. But you could improve it, say, to the space of all reals from 0 to 7. Now it's contractible, so it's a proposition. So you can, in general, if you have a structure, sometimes you can add more to it, and it will become contractible because you will change its geometry. By adding more to it, you change the geometry, it becomes contractible. Yeah? You can think in geometry, you can think of examples like that. Not so hard. Take a triangle, fill it in. Take a circle, fill it in. But also fancier constructions, not just that. Take a space, consider its cone. Topological cone. It's now suddenly a lot simpler than it used to be, homotopically. Okay, so what do we need? So first, we are going to need the notion of a, where am I? Homotopy fiber. Okay, so definition for an F from X to Y and a little y in Y, let the homotopy fiber H fib, so people write this in different ways, I'll write it like this, H fib Fy. This is supposed to be the inverse image. See, this is supposed to be the inverse image of y. So what is the inverse image of y? The inverse image of y is those x's in x such that f of x equals y. But because this is a path space, what will be an element here? Well, an element is going to be x and some path p, where you have f of x, y, and then p is here. And this is all happening in y. So an element here is a pair, x, and a path, which shows that f of x has a path to y. Now that's what a homotopy fiber is. You should compare this to the homotopy fibers that Jaka explained. He used pullbacks and stuff, okay? And it's a very good exercise to understand why this is the same thing as the thing he did. But I think he was also quite explicit in homotopy fibers. He said it's pairs of a point in x and the path going. It was exactly, I mean, at the end, you can do it very generally as pullbacks, or you can do it less generally, concretely, and then it's more or less this. So that's what a homotopy fiber is. So of f at y is the inverse image up to path. There is no other way to define this in homotopy type theory. You see, this is the natural definition. It's the only one. We just simply have no way of saying those x's which f of x precisely maps to y. There is no such thing as precisely maps to y. You have to say such that there is a path, because everything is forced to be homotopy invariant. Okay, and now we define what a homotopy equivalence is. For f from x to y, let is equiv f. This is for every y in y is contour, it's contractible h fib fy. So let's read this. This says, okay, I will read it in several ways, in varying degrees of exactness, correctness. Okay, so one of them says all homotopy fibers of f are contractible. It's slightly inaccurate because I have to say sort of uniformly or continuously in y. Not only does every one of them happen to be contractible, but there is a function from y to this contractibility of its fiber. So I have to say here, I think Jaka would say canonically probably, or continuously in y. Or you could also say, if you read this more set theoretically, the inverse image of every point is a singleton. And this one should immediately suggest that, yeah, this should be a reasonable definition of f is an isomorphism, because one way to say that f is an isomorphism is to say that it's surjective and injective. But I can pack surjective and injective into the following statement. The inverse image of anything is a singleton, because the inverse image of y is a singleton says every y is covered, so it's surjective because, yeah. And it also says the map is injective because there will never be two things mapping to the same y. So does this make such a huge difference? Yes, this makes a huge difference because, as it turns out, we have, and this is not something we can prove in this introductory course, but it's not too difficult, it just takes time, is prop is equiv. And now that I show you this, you should wake up in cold sweat during the night and ask yourself, is prop? That's the thing that should worry you, right? Can a thing be a proposition in more than one way? Because that would be just devil at work, right? If that were the case. Something would be seriously broken if we fail to prove is prop. It better be the case, is prop. Okay, so this is now saying, but being an equivalence is a property. If f is an equivalence, it's an equivalence in at most, so f can be an equivalence in at most one way, so it doesn't matter which way, because they will all be equal. So now we define also the space of equivalences. X, Y is defined. I will write it with words, otherwise it looks weird with all the equal signs. So you say, take those f's from x to y, which happen to be an equivalence, which are equivalences, is equiv f. Also define x isomorphic to y, defined it to be so the same thing but with is iso, which we had earlier, because we want to compare these two. So this is the good one, that this is the bad one. And this is called homotopic equivalence because, well, let's see, because there are many ways to write this type down up to equivalence. Okay, so there are many ways to write down the type of equivalences up to equivalence. This is the original one, and it's also the shortest one. So maybe we need to, let's unfold it a little bit, and let's try to do some basic things with it. Okay. So first of all, let's have some observations. For instance, suppose you want to show that identity is an equivalence. Let's just unpack this to see what it says. Okay. So you want an element of what? You want an element of this type for all x, or let me use the original notation there, for all y in x.
You're not defining any notion.
Oh, sorry, yeah, thank you. What am I doing? Doing this. So this will just be, by definition, unfolding the definition. This is fyx is counter h fib id x at y. And so you work a little more and you get pi yx. Now you need to know is counter by heart. So the is counter says there is a contraction. So the way that so it's contractible space. A space is contractible if it has a center of contraction and then paths leading to it. So there needs to be a point in X such that for all. Oh, wait. Not quite. There needs to be a point. So what is this? Maybe work this out. What is this? So this is sigma x in x such that the identity maps x to y. So it's x equals y. That's what it is. And so now this is saying this thing here now becomes, maybe I don't, so is counter sigma x in x, x equals to y. Okay, so for this we need two things. We need a center of contraction. So we need a point in this space. It doesn't matter which point because they are all equal, but I mean, to get started, you need a good point in this space so that you can then show that all the other points are equal to it. Can somebody give me a point in this space? I need a point of x, I need a point in x, and a path from x to y. Y and the raffle of y. And you see, this is the sort of thing you need to do with your bare brain and hands once go through these little thingies to get used to what's going on. And then you also need, if I take any other point here, so if I take for all, and now a point in this space is a point plus a path, so let me write it down like this. If I take any point z in x and any path p from z to y, then I can get a path from p to y raffle xy. This is what also is needed, and this we'll not do right now, and I think we should do it interactively with people who are interested. Wrong?
Path from Z and
Oh, yes, thank you. So slightly wrong. It's not a path from P, it's a path from the pair ZP. Okay, like that. To Y raffle. Okay. It's not quite induction. You see, you say, I want to do path induction, but unfortunately, Y is not arbitrary, it's fixed. So you cannot just jump to conclusion that you're going to. Do we need a transport? What's wrong? Okay, so I need to take a general point in this space. A general point in this space is a point in x, let's call it z, and a path from z to y, let's call it p. And then this dependent pair is an element of this sum, and it needs to be equal to the other element of the sum, and there is no transport. Yes. Okay, so we have that. So another observation is that every equivalence has an inverse. So suppose I have f from x to y, and I have some c showing me that f is an equivalence. Then I can produce, so let's see, what is this? Okay, what is this c? We have to go look. Is equiv. C is a function, yes? So c, so this is something which takes y in y, okay? And then gives me this horrible is counter business, okay? So is counter h fib f y. So what happens if I apply, so take any y in y and consider c of y. What is c of y? Well, c of y is going to be an element of its counter. So this c of y is going to be a pair of things, and the first component of that pair is going to live where? The first component of is counter is the center of contraction. So this one is an element of h fib fy. And the second component is the thing that's showing that everything is equal to this first one. But what is h fib? H fib is a sum. Where are you? H fib is a sum. So I can take another first component. I will get something in the space at which we're moving. So pi 1 of cy will land in x. So that means that we have the thing which we're going to call f to the minus 1, but this notation is slightly misleading because I'm also using c. Okay, let's discuss this. Okay, so we have f to the minus 1, which takes y to pi 1 cy. And this goes from y to x. So really, you should now ask, hey, this should be called something like inv fc, because it depends on c, not just the f. Correct. It should depend also on c. However, is-equiv is a proposition. So all c's in is-equiv are equal. Therefore, hopefully it doesn't matter too much which C I take. But how much does it matter if I take a different C? If I take a different C while computing this inverse, I will get another inverse, which, however, is equal to the other one. So they will all be connected by paths. So it's not too bad. So people take these shorthands. So really, you need to take the inverse of the fact that something is an equivalence, not just the map itself. But this is just a shorthand. Would be better. Okay, better. And then when you have a proof assistant, you have trickery so that you can most of the time leave out the C. Okay, and that's how you get an inverse. And then it turns out, using all the other structure, and this is calculated in various places, the notes that I gave you, the hot book, the notes I linked to, it turns out that f to the minus 1 is an inverse of f. So we have, and also that f to the minus 1 itself is an equivalence again. So what we get? So we now see that if you have an equivalence, so first of all we see that x is always equivalent to itself via the identity map. Then we see that if you have an equivalence from x to y, you can get an equivalence from y to x. Okay? But let us improve on this. Better to say, this is what you should start asking. It's one thing to say that there is a map from the first space to the second space, and a map going back, or even say that they're isomorphic. But it's the best to say that they're equivalent. If you can say they're equivalent, that's going to be very nice, especially since we're eventually going to have the univalence axiom, which says that equivalent spaces are equal. And that's going to be very, very nice. So we should strive to use equivalences whenever we can. Okay? We also get, by the way, that if you have an equivalence from x to y, and then you have an equivalence from y to z, you get an equivalence from x to z. Okay. And so let's practice. Would anybody like to remark anything about my last statement? You should remark something about it. I said, if this is equivalent to that, and this is equivalent to that, then that's equivalent to that. What you should ask is, which equivalence do you have in mind? Because there can be many equivalences from x to y. So really what I want to say is the one that is induced by composition of functions. So if f, what you really show is that if f is an equivalence and g is an equivalence, then the composition is also an equivalence. That's what you really want. And this can be made all very precise. Let me try to concentrate on on this important, maybe this. We now have what is the relationship between isomorphism and equivalence? Okay, so first of all, up here, you see, if we started with an equivalence f, we start with an element of equivalence from x to y, and we get an inverse of f. So one thing that we can get is this: if the spaces x and y are equivalent, then they're isomorphic, because an equivalence is an isomorphism. So, or more generally, is equiv f, well, the same thing, is equiv f, then is iso f. Okay? The other way around, yes, the other way around also holds. also we have, if you have an isomorphism, then you get an equivalence. There is a way to, if you have an isomorphism, so let's see, what is, so every isomorphism can be turned into equivalence. If it has an inverse, you can show that its homotopy fibers are contractible. So you can always show that. But these two maps here are not in general inverses of each other. So we do not in general have that isomorphism and equivalence are the same thing. So one wonders then, why is it the case that this stuff doesn't come up in ordinary mathematics? Nobody cares about equivalences in ordinary mathematics, but somehow here it's making a difference. So that's explained by the following theorem. If P and Q are propositions, then to say that they're equivalent as spaces is equivalent to saying that you have a map from P to Q and a map from Q to P. And B, if X, Y are sets, then X is equivalent to Y is equivalent to saying that they're isomorphic. So, as long as you're only talking about logic and sets, it really doesn't matter, because homotopy equivalence for propositions is the same thing as logical equivalence for propositions, and isomorphism of sets is the same thing as equivalence of sets. So we are just generalizing the usual notions. The thing that we've achieved is that we generalize this notion in such a way that it's still a property. It's not accidentally a structure. Isomorphism, being an isomorphism is structure, but being an equivalence is not, is a proposition. So we're going to end here, and next time I'm going to say a little more about equivalences, because I would like to show you another formulation of the fact that something is equivalence, which also sheds light on why isomorphism is not a proposition. Being an isomorphism is not a property. And then I would like to show you how to use equivalences to speak about universal properties. So universal properties of mathematical objects are very important because they, you define things using universal properties. For instance, you define one way to characterize the real numbers is as the completion of rational numbers, and that's a universal property. Another one would be to explain what is a pullback. A pullback has a universal property. It's a square such that if for every other square there exists a unique la 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 la, and all of these are nicely phrased by saying that certain maps are equivalences, and this packs the entire universal property into a nice statement that something is an equivalence. So this should be of some interest to homotopy theorists, because they are now sort of, their tools like pullbacks and other notions that you would use are now suddenly subject to homotopy theoretic methodology. And so that ought to be interesting. I don't know if it is interesting, but for homotopy theorists, it certainly excites people who do computer science and they learn a little bit of homotopy theory. Okay, so next time we do a little more of this. Thank you. We should discuss how to do these details, by the way. There's lots and lots of theorems and details. And I don't think you can feel the subject unless you do some of this. I'm inclined to give you some of these as homework because I shouldn't be giving you open problems as homework. But on the other hand, even such little details that are just left out here may be quite a stumbling block because it's weird stuff. It's a different way of doing mathematics. So we need to figure out how to organize some sort of a session or something where people can show up, and maybe I give you some examples, some warm-up examples and some homework, and then we do the warm-up examples together so that you can go on. I really don't want, otherwise I'm afraid too many people will feel like they're just fish out of the water. Okay, thank you.